Alrighty, guys. My name is Mike, and this is the weekly stack. These are typically hosted by myself and Zach. However, um, you guys missed the first three recordings, so we are going to do just a little re-record, get the YouTube channel established, and then after that, all sessions will be on Tuesday around 8 p.m. Mountain Time. Um, and it will be live stream on YouTube. So whether you're in the Discord channel or on the YouTube for the live stream, I encourage you guys to participate. I will open it up for discussion, ask questions, things like that. I encourage you guys to join in. But for these first three videos, it's just going to be very quick, straight to the point. Um, just kind of laying out what we went over real fast. Um, if you have any questions, please feel free to reach out to me. We can always have a private chat and go over anything more. Always feel free to also leave, any topics that you'd like to hear in the future sessions, and I'll make sure I cover that. Session three, we actually had a principal engineer join, who is absolutely fantastic. Thank you again for him to join. Um, but without further ado, we know we're gonna get started. You will see me looking down from time to time. I do have a bunch of notes because 3 sessions of recording is it's a lot. It's a lot. It's a lot. So, like I said, these will be a lot more dynamic in the live streams, but these are going to be pretty, just very informative as we roll through this stuff. So, yeah, let's start with big O notation. Um, so this is how we measure speed and efficiency. Um, O of 1, speed of light, O of n, linear time, fast but not as fast. Check every name but don't know the position. Um, O of n squared is quadratic time. It's like biking from New York to California, like a class of students having to shake hands with every student, like 10 times 10, 100 times 100. Really slow. Pretty bad. Typically a better solution. And then we have log of n, which is like your speed of sound, like a dictionary. Before it's kind of like if you open up a dictionary and you're looking for a specific word, it'd be like flipping from before and after that letter. Like if you're looking for the letter N and you open up the book and it lands on O, all right, we now know that we need to flip forward, okay, and then vice versa. Essentially cutting time by half, then half again, then half. Um, and that's nice little visual representation. Of course, O of 1 being fastest, speed of light, speed of sound, like walking and like biking from here in New York. Alrighty, alrighty. Now we're gonna move on to arrays. Let's see, I have an array one around here somewhere. Right here. Ooh, big boy. Well, here's what it looks like. We're gonna swap to here. All right. Array. Arrays, they're like kind of like a row of lockers. They have fixed positions, indexes that you can identify them continually side by side. When filled up, they need to be copied over and made into a new array if you want to add new positions. Typically, we have an O of 1 for accessing and replacing indices because we're able to grab them right from their name. However, insertion and deletion is O of n because again, we'd have to copy over, restart that whole new array. It's harder to just kind of just yank those things out of there. Um, Linked list, that's what we're going to move to next. Again, here's just a quick little example of the arrays. Um, you know, this array is numbered. And arrays always start at 0. That's a big one. Starting at 0, go 0, 1, 2, 3, 4, 5, and then those are the indexes, and then the elements would then there be inside. Alrighty, let's drop that one off the board. Linked lists. Alrighty, these are like train cars. You typically go from one car to the next. They are stored in separate nodes. They are more flexible than arrays. Easily add or remove elements. You don't have to copy over and repaste like you do. Accessing is slower though. O of n is going to be your accessing as well as if you are searching. Alrighty. Um, Whereas if you have the reference, adding with references, O of 1 is going to be like accessing with indices. Let's see, where is our linked list? Here we go. So you can see it even looks like a little train car is moving from one to the next. So as long as you have those reference numbers, you can get right to it. Otherwise, yeah, you're walking from one car to the next. Very linear. Um, you know, bringing us back to here. Very linear. O of n. Sorry that the colors are different on that. I just noticed that too. But it's okay. It's okay. Next, moving down to stack. It's going to be like a stack of chips, like a thing of Pringles. Um, let's see where we're at with that. Stacks, boom. As you can see, this is also where we hit our uh, our last in, last out. As you can see, it's at the bottom, so it'll be taken out last. Alrighty. So generally, if it comes in last, like if you put 3 in last in, it's coming out first. So last in, first out. Last in, first out. However, when that keeps getting stacked on them, the last in number changes. So last in wasn't just the 1, now it's 2, then it's 3. So last in was 3, so first out 2. Then 2 would be pulled, then so on. Okay? So quick little representation. I'll show you guys that one more at the end. You can only grab from the top. This is great for DFS, which stands for Deep First Search. Alrighty, right here. Now searching typically, like our pop and our push is a O of 1 because it's right at the very top. However, searching is O of n because we do have to go through the stack. Now, deep first search. This is where we will be going down the node, checking, then backtrack to the unvisited neighbor. Okay, I have a little chart for here too, so it's a little blurry. So, but you can see we start with the initial. We go deep first, so we're going down, 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 down. Then we track to the invisited neighbor, then back up to the next invisited neighbor. So since we went here, it has nothing below it. So then after checking here, the next one to check logically is here. And then instead of going to its neighbor, we go deep again, as deep as we can, then to the neighbor. Back up, deep again, and just so on and so forth until we hit our goal. Deep first search. Alrighty. Now, deep first search. This can also be used in quite a few things, which I will cover here in a minute. Let's see where we got. Sorry, one second. On stacks, deep first search. Yeah. Sorry, notes are a little jumbled. Alrighty. Go deep, backtrack, check on visiting neighbors. Stacks very useful. Next, moving on to queues. Queues. Alrighty. Queues. Add at the back, remove from the front. Add it back, remove from front. It's kind of like pushing, like changing stock. Like if you're in a restaurant, making sure things get rotated, adding from the back, moving from front, right? This is going to be your first in, first out. See, they're coming in first. 6 at the beginning had been 1, and then it would have been pushed through, added right to the back. So first in, and then be taken out first. Typically, this is how Spotify's play queue works. This is also used with breadth first search. This is another great one. I'm about to pull up in a second. I got so many layers going over here, guys. Alright, let's see. Before we get to breadth first search. So, queues, just like a grocery line, y'all. Only add in the back, remove from the front. Just like a stack, cannot access by index. If needed, it would be O of n going through each one. If not, first one. The first one, of course, O of 1, because you're right there. It's the very first one, right? Um, let's see. Otherwise, O of 1, like stack, but reverse. Um, highly used in Spotify and breadth first search. Explores the full width of a node tree before going deeper, and that is our breadth search first. Um, it's Here we are. Um, I think this thing is sorry. Alrighty, so that's for search. So we're starting here. It's the opposite of the deep first search. So we'll check the entire row, come down, check across, and go down, check across again. Whereas deep first search would be coming down here, over, jump up, down, over, jump up. All right, it's going to check the whole. It'll check the whole row first. The opposite of deep first. So here's breadth first. Here's deep search. So again, you see the difference. Um, so essentially, breadth first search, this would be used for like Spotify, things like that, whereas deep first search would be more used for like web graphs, game states, DOM trees, that sort of thing. Just trying to search through them. All right, let's pop these off. These little bad boys. Um, Again, there's your queues photo. Now, a heap or priority queue, or as I also like to call them, because there's two types of heaps, min heap or max heap. Essentially, you want to think of like a stack of boxes where the smallest box is on top, um, and that's going to be your min heap. Um, Always need a box at the top. It's not a heap or a priority queue if that is not the case. Here we go, min heap and max heap. Alrighty. Um, if any box is removed, they need to readjust so they have one at top. The two different types of heaps, min versus max. Min, where every parent is smaller than its child, as you can see 10, then 15, then 40, 15, 40, and 50, and so on. Lower number on top, where max heap, where every parent is larger than its child, higher number on top. As you can see the decreasing values. For efficiency purposes, O1 for the top elements and O of n for every other element, because of course if you're right at the top, you can grab that first top element, boom, done. But then you have to traverse down through each one, which is not ideal for lookup. Um, Adding, it will be an O log of n. Um, Yep. Adding is an O log of n, bubbling up to its correct position. Because if, like, say, you added, say, a 14 in here, and I put the 14 here, obviously it would then bubble up here, having to readjust. It won't be as linear, but it won't be as fast as light. Essentially, a balanced binary tree. Um, these are good for using for scheduling tasks, task scheduling. Um, yeah, remove a box, the rest rebalance so that there's always one on top. And there's lookups, and there's all of your everything we just discussed. Hash mapping. Ooh, gotta love hash mapping. Hash mapping's a big one, yo. Let's take that off the list. Alrighty, hash maps. Here's a good look at it. I know these ones can be a little bit more confusing. You have keys, and you have hashes, and the hash function that goes between. Alright? So, let's think of like a mailroom in an office. Everyone has a mailbox. Um, Storing data uses key value pairs. Each key runs through a hash function and finds where it's stored. Um, Looking things up is O of 1, as well as insertion. It is like the speed of light when it comes to looking those things up. Um, unless too many items share that same key. It just worst case scenario, it will become O of n with collision cases. But typically it will be an O of 1 function. Alrighty, again, here's your keys, where it's stored in the hash function. That's off the list. Binary trees. So each node follows a specific order rule. The left child has to have smaller values than its parent, whereas the right child has to have greater values than its parent. Access, insertion, deletion, these are going to be O log of n, going through the dictionary by half essentially, just chopping down through this tree. Um, if the tree is unbalanced, it'll be more like linked list. Is now with O of n because you have to check each element. Um, Unbalanced just degrades you to O of n. I mean, because you're unable to cut through half. Because I mean, let's look at this. If you're missing one of these elements, how are you able to cut through half if you're missing one? It's odd. It's a non-number. You can't. But as you can see here, even starting at the top with 11, you have 17 and 15. Okay, going to the left, smaller. To the right, higher. You're starting to able to figure out how to write these binary trees. So when we're looking at some of these other structured lists, some of these other binary trees for data structures, a lot of them are binary trees. However, you were searching through them in different ways, at least when in terms of structure. Like a min heap. Could definitely be a type of binary tree because you have a lower value on top. Guess not really, because yeah, you have a lower value on top and then it would stay going low, or it would go high on the left. Yeah, so I don't know. There's some thoughts there. Like I definitely have some thinking to do on that. Like I said, I'm not perfect. Definitely have some thinking, but I mean, in general, binary search tree, start with your top node, then split left or right, left being low, right being high. Pop that bad guy out of there. Stacks. I showed stacks. We just didn't delete it. Sorry. Trying to make sure I'm on the right path. Now sets. Sets I don't really have an image for. Best way to describe sets is thinking of like Thanos' gauntlet, right? It can hold powerful stones, but each one is unique. You cannot add the same stone twice, so everything has to be unique. Um, Only one of a kind. Only one of each kind. Order does not matter. Good for searching through trees and graphs to keep track of visiting nodes. Um, I mean, the full definition of it here is an unordered collection of unique elements, typically implemented using a hash table. Using hash maps. Um, if you're checking for an element, that's going to be your O of 1. You know, uh, issues hash functions and hash maps take it up to an ON, unfortunately. Um, Big with tech interviews, um, remove duplicates, or big with tech interviews. Using sets has been known to help like find and remove duplicates because again you can't have the same set twice. They are unique, so it's able to find duplicates and get those removed. Or checking for a certain membership, making sure that that they are indeed into the system and that they're not accidentally implementing second user data that's already been added in there. Um, this is typically, an O of 1 process. Unless there is some sort of collision, then yeah, of course, it will be dropped down to O of N. But, hash mapping, hashing, and sets, I mean, almost all of these data structures are very big through, tech interviews. You want to know what these are. You want to know how they're used, at least what they look like. So that way, when you're thinking about these structures and thinking about what you want to use when building algorithms, you know what you're doing. Knowing that, okay, using an array might be good if I'm wanting to access things, but do I really want to use it if I'm, inserting or deleting? Maybe I want to use a stack or a queue or even a binary tree. You know, like personally, I'd use hash maps because look right here, looking up and inserting O of 1 versus an array, which is O of N. I mean, th this is just something great to always have on hand. I will again be including, I do have some, let's see, I do have a resources channel in here where I have a lot of my notes as well from some things that I just told you guys today, as well as some of the photos. Please, let me know if you'd like to be a part of it. I am going to start posting mermaid charts, so you can also be able to look through the notes a lot faster and cleaner. Um, I'm here to help guys. I'm here to help you guys learn, and I really hope that this first video was good and up to y'all's par. Um, so yeah, I'm really looking forward to the next video that I'm due and get uploaded, and hopefully have all three done before Tuesday. Um, I got a bunch of coding to do of my own as well. But yeah, I hope you guys enjoyed this video. The next one is on UI and UX and how it pairs with software engineering. I'm going to go over some of my projects that I've done. Through my boot camp and the ones that I won with my code jam, as well as the one that I didn't in my coding competition. So I'm really excited to show you guys that, kind of go through that. I'm really excited to have other areas of tech also join these talks, UI, data, everything. So without further ado, it was a great time, and I will see you guys in the next one.